Okay. Good afternoon. Welcome to the last lecture, officially. So just start out, I guess as a group, I guess you did okay, but yeah, I guess this last quiz must have been a little more difficult. I think a lot of you had difficulties with the BJT question, so I'll try to review a little bit today, but I'll definitely cover that in the review session. So the average score is here, showing that it was a little bit lower, but a little bit higher than for quiz 2. So in this distribution chart, the darkest bar, so that's black. Black is quiz 6. So you can see the average is a little bit lower than in the previous quizzes. But remember, I'm going to be dropping your lowest quiz score and determining your course grade. Okay, so a few announcements. So next week, Tuesday and Thursday, we'll be here as usual, but really just project presentations by the graduate students. And the schedule has already been posted on the course website. And undergrad students, of course, are welcome to attend any of them if they wish. The final exam will be held on the 17th at 8 a.m. In 120 Latimer. So I hope you look that up before, well in advance. Okay, so I guess we'll start roughly at 8 o'clock. I don't know if we usually start 10 minutes after. But anyway, let's try to show up at 8 o'clock and start the exam on time. So it's going to be 3 hours long, probably just 6 questions, similar to the quizzes. So each quiz was about half an hour long, right? Less than half an hour long. So you should expect something like equivalent to 6 quiz questions, or 6 quizzes as the final exam. And it'll cover the BJT, okay? So it's covering the entire content of the course. Yes, Louis? Okay, so the question is, what's the best way to prepare for the final exam? Well, hopefully throughout the semester you've been preparing with these quizzes, but really the questions will be similar to the kinds of questions you've seen on the quizzes. So the only thing you haven't seen yet really is too much of BJT questions. So I'll make sure that we have some sample questions posted on the website for the BJT. Okay. So we'll allow you one more page of notes to cover the BJT, and I think that's it. I'm not sure. I'm not sure about calculators. I mean, do people feel strongly that they would like to have a calculator allowed on the final exam? Because if so, then I'll be free to take off points for any numerical errors. I mean, okay, nobody really wants, okay, that's fine. All right, yeah, generally we haven't taken off points unless it's really obvious. I did end up taking off half a point for people who didn't calculate beta properly, because I think that was a little bit easy, so it shouldn't have been that hard. But other than that, generally we're pretty lenient on calculations, hand calculations. Okay, so next Thursday I'll hold a review session starting at 3:30. It likely will be in this classroom or the one next door. I've allocated 2 hours for it. So I'll probably cover the course content, 6 topics, right? Well, I'm not going to cover semiconductor fundamentals because I think you should know that. But just roughly 20 minutes. If we want to come for only part of that, you can just assume I'm going to spend roughly 20 minutes for each general topic. Okay, so that's metal semiconductor contacts, p-n junctions, MOS capacitor, MOSFET, BJT. Oh, that's only 5. Okay, I guess maybe I'll review semiconductor fundamentals. Okay. Anyway, so we'll announce the room on the website shortly. Okay. Any other questions regarding the logistics for the remainder of this course? Okay. So let's review, since actually so many of you didn't get the BJT question correct. I just wanted to review. Okay. So let's review just to spend a few minutes. So let's look at a p-n junction diode. Okay. We have let's say p-n diode, and we have metal contacts. So holes are entering. So let's say this is the emitter, of a BJT, and this is the base region of a BJT. So at the contact to the emitter, we have holes going in. Some of those holes recombine. So they recombine with electrons. Okay, so the holes that enter, I'm going to draw the metal contact for the base region out here. So we have electrons coming in. Right? So remember, in a metal semiconductor contact, you only have majority carriers flowing in or out. Okay, so for a p-type contact, you have holes flowing in under forward bias. And for an n-type contact, you have electrons flowing in. So some of these electrons that flow in end up diffusing across the junction. And after they diffuse across the junction, they recombine with holes. So some of the holes that are supplied to the emitter recombine with electrons. The remaining holes actually diffuse into the base region. Okay, so you have diffusion of holes across the junction. We have recombination of holes in the quasi-neutral emitter. Okay, so let me just draw this. So we have current I sub B. If electrons are flowing in, then I sub B is positive flowing out. If holes are flowing into the emitter, then I sub E is positive flowing in. Okay, so it turns out then for a BJT, you have another p-n junction here with a depletion region. Okay, and if the width of the base is very short compared to the, okay, so there's a depletion region here as well. So if the width of the quasi-neutral base is short compared to the average distance a hole travels before it recombines, then actually all of this diffusion current, or most of it, will just be collected by the collector. So those holes will end up flowing out and constitute the collector current. So you can think of, okay, so the collector current is really just that component of the emitter hole current that actually diffuses into the base, okay? And so let's assume that there's not much recombination in the base. And then the base current is usually nowadays primarily due to electrons diffusing across. So okay, so the electron, let me just change colors here. So this electron current, part of it diffuses across, part of it recombines with holes in the base. But hopefully this is like negligible. Okay. So this base current really is comprised of I is equal to IEN. In other words, most of the current that has to flow into the base contact is supplying electrons to diffuse across the junction into the emitter. Okay. So the emitter current is really just equal to this this base current, which is mainly due to electron diffusion, and it's equal to okay. So it's equal to the electron current plus the hole current going in the opposite direction. Okay, but that hole current mostly ends up as collector current. So this is how you get IE equals IB plus IC. So this is really the electron diffusion component, and this is hole diffusion component. Okay. So this is hole diffusion across the emitter junction that ends up being collected by the collector. Okay, so one thing I didn't really, in those complicated equations that we derived, if you actually simplify it for, if you go back, okay, if you go back and look at, let's just go back and look at the lecture notes. I think it was lecture 20, was it 21? It's 25. No, 26, hold on. Back and look at the equations. Okay, so these really long equations. Okay, so right here, so that look, if you look at this equation for the collector current, so if W is much less than LB, in other words, if the width of the quasi-neutral base region is much shorter than the diffusion length, average diffusion length, then this term actually just becomes dB over, I'm going to write it on the board. It's just going to be dB over WB, sorry, W, yeah, dB over W times PB naught, but PB naught is just the minority carrier diffusion, minority carrier concentration in equilibrium. So that's Ni squared over NB. Okay, so that's basically, and then this term turns out to be dominant. Okay, so this term over here, see the collector base junction in active mode is usually reverse biased. So this term basically goes to 0, and then this whole term is actually negligible compared to this first term. So the collector current, let me just write it, summarize it here, is basically going to be approximately QA times dB over W Ni squared over NB times e to the QVEB over KT minus 1. Okay. So hopefully you can, so that simple equation here, this is the component of the emitter junction current that's due to hole diffusion across the junction. Okay. Now so the difference between IE and IC is actually, if you compare, is really right here, right? So this term constitutes mostly IB. Okay, so remember IE is equal to IC plus IB. So this is the, so what I circle here is IB, and over here, the second term here, that's IC, pretty much IC, right? Okay, so this is IC and IB. Okay, so if you want the gain of your transistor to be high, you want IC over IB to be large. And what that means is that the ratio of the hole diffusion into the base to the emitter, electron diffusion into the emitter, that ratio has to be high. Okay, so that's why you have to dope the emitter more heavily than the base to get that ratio of holes diffusing across the junction. So holes diffusing across the junction have to be much greater than electrons diffusing across the junction in order for IC to be much larger than IB. Okay? So if you increase the doping in the base, you're actually changing that ratio, and you're favoring more electrons to be diffusing into the emitter, and that's not good for the. So that's what we call the injection efficiency or emitter efficiency. That degrades emitter efficiency. So emitter efficiency is just basically, okay, how well does the emitter act to supply minority carriers to the base rather than wasting current due to minority carriers diffusing from the base to the emitter, right? Because only carriers diffusing into the base are going to be collected by the collector. Okay? Okay, so that's just very qualitative. But we're going to come back and use the simplified equation today, which is why I went through this. So any just qualitative questions about how the PN junction, the BJT, in the active mode, how the gain depends on doping and things like this? Okay. Okay, so let's go back and look. Let's continue where we left off last time. So this is a modern BJT structure. As I mentioned, to form this emitter region here, to avoid having a lot of crystalline defects in this silicon emitter region, basically we form that by depositing a doped layer of not really single crystalline silicon, but this polycrystalline silicon on top of silicon, and then we diffuse N-type dopants into the surface to form the single crystal emitter region. So just qualitatively, I just wanted to mention that, well, okay, so let's review. If we want the ratio, okay, let's see. If we want to minimize electrons diffusing across the junction from the base to the emitter, do we want to have a long emitter or a short emitter? Short. Okay, so if we have a short emitter, that will force the electron concentration to go to 0 at the emitter contact. And so what will that do to the concentration gradient is shown here? If we have if we make this emitter really short, it will force the electron concentration to go, the minority carrier electron concentration to go to 0 in a shorter distance. So the concentration gradient gets steeper. So electron diffusion current, so the diffusion of the rate at which electrons diffuse from the base into the emitter will increase. Okay, is that good or bad for injection efficiency or emitter efficiency? It's bad, right? Yeah, so it turns out that the polycrystalline silicon emitter is actually good in a sense that the mobility, okay, so let me write this down. So the carrier mobilities in polysilicon are lower than in crystalline silicon. Okay, so polycrystalline silicon, okay, so there's a question on Piazza. So polycrystalline would be like, let's say in this room, you have chairs arranged kind of neatly in rows. Okay, if it were, so that's kind of like a crystalline structure. It's very orderly, right? There's some long-range order in the way you arrange the chairs. The analogy for polycrystalline would be, okay, maybe chairs are arranged orderly in one part of the room, and they're orderly in another part of the room, but they're not all coordinated. You know, so you have like rows that aren't all lined up across the classroom. So if you want to walk quickly through from one side of the room to the other, it would be harder. You'd be less mobile if the chairs were not, you know, arranged uniformly throughout the length of the classroom, and they're only locally arranged uniformly. So same thing, the mobilities, electron mobility, hole mobility is going to be worse in polycrystalline silicon than in single crystalline silicon. And so this means that the diffusion coefficients are lower as well, right, due to the Einstein relationship. Okay, so the diffusion current, though, right, diffusion current is proportional not only to the diffusivity, okay, let's say d sub n for electrons, but it's also proportional to the concentration gradient, right? So the excess electron concentration as a function of distance. Okay. So if we have single crystalline silicon, like in this polysilicon emitter structure, so we have single crystalline silicon contacted by equally doped polycrystalline silicon, you have to have continuity of current. Okay, so the rate at which carriers are flowing like through the polysilicon should be the same as the rate at which they're flowing through the single crystalline silicon. But the mobility is lower in the polycrystalline silicon. So what that means is that the concentration gradient must be steeper in the polysilicon too, so that the diffusion current in the silicon is equal to the diffusion current in the polycrystalline silicon. And so what this means then is if you compare a single crystalline emitter versus a polycrystalline silicon in series with single crystalline silicon, so these are the same widths, right? This width here is the same as the width here. You can see that the slope at the interface, okay, the slope at the edge of the depletion region, that slope is what determines the electron diffusion current going in from the base to the emitter. Okay, so this slope is shallower, right? Shallower slope, and so that means we have smaller IEN, right? So that's good for gain. I mean, that's good for the emitter efficiency. So that's one benefit of a polysilicon emitter structure. So qualitatively, you should know that the polysilicon emitter is good for, I mean, it's just practical for achieving a low defect emitter base junction, but it also has this benefit that you effectively have a wider, I mean, this is equivalent to having a much wider, right, single crystalline emitter, right? If you had this kind of slope, that's kind of equivalent to having a much thicker single crystalline silicon emitter. But you don't need to make it, but then that'd be kind of more resistive and so on. Okay, so the benefit is that you can have higher current gain, higher emitter efficiency with the structure as well. Okay, any qualitative questions? Yes. So the question is, well, okay, why don't we make it amorphous silicon? Yes, okay. So the mobility of electrons in heavily doped polysilicon is on the order of about less than 50. Well, actually, it's like, yeah, on the order of 50 or less, tens. In single crystalline silicon, it could be like 100, right? Amorphous silicon is like 1. Okay, so yes, so I guess you could make it amorphous, but practically during the fabrication process, if you deposit amorphous silicon on single crystalline silicon, it will sort of, because of the high temperature involved, it will naturally crystallize. Yeah. And amorphous silicon having such low mobility will be more resistive, so you'll have more emitter series resistance, which might not be desirable. Okay, so last time we introduced Gummel number. This is not so important for you to, I mean, it's just how do you account for the polysilicon emitter structure if you want to use simple Gummel numbers to estimate gain and so on. So don't worry about that. Okay, it's not. I'm not going to ask you about that. All right. Okay, so that's it for a modern structure. Actually, the most commonly used high-performance BJTs today are actually heterojunction BJTs. So let me explain why this is the case. So, you know, we'd like to dope the emitter much more heavily than the base, and the base has to be doped more heavily than the collector to minimize the base width modulation effect. So that means the emitter has to be doped pretty heavily. But if we dope the emitter very heavily, then there's going to be band gap narrowing. And so that's going to increase the intrinsic carrier concentration in the emitter. And that's actually counterproductive to gain, right? Let me think. Yeah, okay. I'm not sure. Hopefully, okay. So I don't want to go all the way back there, but let's see. Let me go back and look at the, I think it was the diode. Okay, so this is just to remind you, a diode under forward bias, you have excess minority carriers whose concentration decays exponentially. This is a log plot, so it looks like a straight line here. All right, so the excess minority carrier concentration at the edges of the depletion region, they depend on Ni squared. Okay, and the higher the excess minority carrier concentrations at the edge of the depletion region, the more concentration gradient you have, because you go from that concentration to 0, essentially, right? Excess carrier concentration to 0 at the edge in the quasi-neutral region. Okay, so if Ni squared, if the band gap is narrower, then, okay, so let's say this is the emitter on the left. So if Ni squared, if the band gap is narrower, then Ni squared will be higher. And so you'll see the excess minority carriers in the emitter on the left go up, and that will cause, that basically results in more, that means there's more electron diffusion current going into the emitter, which is bad for emitter injection efficiency. Okay, so that's bad. But what we can do, is we can counteract that by increasing Ni squared in the base. Okay, so that's exactly, so how do we do that? We do that by using a base material with small band gap. Okay, So that's basically, that's the whole idea. So if we can actually have a base material with a band gap that's smaller than the silicon band gap by some delta EG. Oh, sorry. Okay, so this is bad. Okay, so if we can do this, then we can enhance Ni by this exponential e to the, that exponential factor. Okay, so it turns out, fortunately, that silicon germanium, so it's an alloy of silicon and germanium, will have a smaller band gap because germanium has a smaller band gap than silicon. So an alloy of germanium and silicon will have a smaller band gap than silicon. So for example, if the concentration of germanium is, or the mole fraction, or the concentration of germanium is 20%, then the band gap is smaller by about 0.1 electron volts. Okay. Well, let's just say, for example, if delta Eg is equal to 0.12 electron volts, well, okay, I'm not gonna, yeah, I mean that's basically I think it's one order of magnitude, right? Okay, bottom line is if you have smaller band gap in the base, then you have higher Ni squared in the base, and that enhances your current gain. Okay, but what's nice about that is that, what it allows you to do is, okay, well, if Ni squared can be increased, let's say, by orders of magnitude, that allows us to increase Nb, the base doping concentration, and still have a beta that's pretty high. Okay, and that's advantageous because then we can reduce the parasitic base resistance and also reduce the bandwidth, the base width modulation effect. So that means we can increase the early voltage, have flatter IV curves in the active mode, and that gives higher performance, higher gain for amplifier applications. Okay, so really the big benefit of a silicon germanium base BJT is that you can have high gain with high base doping. Okay, that's okay. So you should remember that. And then the speed actually improves, and I'll explain why in the following slide. So this is a cross-sectional micrograph, where the colors have been added, so they're artificially added, and then the isolation. Yeah. Okay. So they etched away some stuff to highlight the different regions. But anyway, you can see the emitter. So the BJT is just really right here. And the silicon germanium is just a very thin layer that's grown epitaxially, single crystal on top of silicon. And then the single crystal emitter is grown right on top of that. So these are really, really thin layers here. Okay, so there's two cases. The simple case is if the germanium concentration is uniform in the base, and the second case is what people use today. They actually grade the germanium concentration. So you have, let me make sure I don't mismark this. So we have increasing germanium concentration towards the collector. So you have basically, look at the band gap energy. The band gap here in red is decreasing as you go from the emitter to the collector. Okay. Now the base is uniformly doped p-type. Okay. So basically, the Fermi level and the valence band edge are fixed like this in the base region. And if you're changing the band gap, basically what that means is that you're changing the position of the conduction band edge. Okay? So that results in a built-in electric field. The built-in electric field is pointing this way. So does that help or hurt holes that are diffusing from the emitter, from the base into the collector? To help. Did I just draw that wrong? That's funny. Oh, I'm sorry. Okay. This is only done for NPN, that's why, okay. So this is, okay. This only works for NPN. And the reason is because if we look at the energy band diagram for silicon and for silicon germanium, okay, well, let's just draw it this way. For silicon, we have an electron affinity that's about 4, just very roughly 4 eV, and the band gap energy of 1.12 eV. So that's for silicon. For germanium, silicon germanium, the electron affinity is also about very roughly 4 eV, and the band gap is less than 1.12 eV. So basically, if you want to grow silicon germanium on top of silicon, the conduction band actually lines up pretty well. And what you end up with is a discontinuity in the valence band position when you go from silicon to silicon germanium. So what that means is that actually, so that means if you have silicon and silicon, if you have a silicon germanium junction, it's pretty easy for electrons to go back and forth between the silicon and silicon germanium. It's not easy for holes to go back and forth between silicon and silicon germanium because you need more. Basically, there's a potential barrier. You need to give the holes kinetic energy to be able to enter the silicon. Okay, so it turns out then that it is nice to use this band heterostructure if you want to favor electrons injecting from the silicon into the silicon germanium, and you want to block holes diffusing from the silicon germanium into the silicon. So that means that this is only favorable for an NPN bipolar transistor. Okay, so let me write that down here. So it's N plus silicon emitter. And then we have a P-type silicon germanium base and an N-type silicon collector. Okay, that makes sense now. All right, so in this NPN BJT in active mode, so remember, so the emitter junction is forward biased, so the potential barrier to diffusion is reduced a little bit, so you can have holes diffusing as well as electrons diffusing into the base as well as holes diffusing into the emitter. And then in the collector, you have this reverse bias, so you have large band bending across the collector junction. Okay, so we have this discontinuity in the valence band only. Okay, not in the conduction band. Okay, so the key here, though, to notice, it's not really drawn clearly here, maybe in the upper diagram. So the benefit of having silicon germanium instead of silicon in the base is really the difference between these two curves. So let me highlight that. So this is for silicon. Okay, so what's drawn here is energy band diagrams for an NPN transistor in active mode. So the black is for silicon, and then the blue, these are for silicon germanium base. Okay, so this is silicon base, and the blue curves are for silicon germanium base. So for the same applied voltage difference between the base and the emitter, you see this QVBE is the same for those two different cases. You can see the barrier for electron diffusion is lower for the heterojunction bipolar transistor. Okay, whereas the barrier for hole diffusion is similar, is the same for those two transistors. Okay, so basically you're making the barrier for diffusion lower for electrons than for holes. So you're favoring electrons going into the base. In other words, you're enhancing the emitter efficiency, injection efficiency. Okay, and we can retain that benefit by having germanium, some germanium at the near the emitter junction, but then we can also increase the germanium concentration as we go towards the collector. So we have a built-in electric field, and that electric field helps, so electrons like to drift downhill, right? So basically that electric field will speed up the rate at which electrons move across the base and are collected. So you can speed up the operation. In other words, this transistor can operate at higher, can respond to higher or faster signals or faster changes in the applied current or applied voltage. Yes, Ali? Yeah, so the question is, how can you have an E field that, see, that's a good question. The electric field only exists for electrons. It does not exist for holes. Right, how? That's how. Okay, so that's a good question. So how, well, we do it by grading the concentration, I mean the composition, right? So you're basically changing the semiconductor material so that electrons prefer to be in the higher germanium concentration material. Because you can think of it as similar to like work function changing. Like the electrons will want to naturally be in a larger work function material, lower energy. So in practice, that's how we do it. You can actually, just like when you form a p-n junction, you're engineering the work function of the two materials, and so you have a built-in electric field in a p-n junction, right? You're having a change in materials, essentially. You're going from n-type material to p-type material. Here, you're just changing the composition to change the band gap instead of like the work function. Well, it is truly a built-in electric field. Just like in a p-n junction, you have a built-in electric field. Yeah. Yes, question?
But then wouldn't, if the holes...
But yeah, so the question is, well, wouldn't the holes want to go from one in the opposite direction? Well, that's the interesting thing, is that the electric field only is seen, or this drop in potential energy is only seen by electrons, not by holes, right? For holes, the potential energy is the same throughout the base, the quasi-neutral base. Okay? All right, so qualitatively, you just need to know that with a smaller band gap base material, it just turns out for the silicon germanium material system, all of that difference in the valence band, in the band gap actually shows up for the valence band only, right? So the key is that you see a difference in valence band energy between silicon and silicon germanium. There's really negligible conduction band energy difference between silicon and silicon germanium. Okay, so this is why it only works for NPN BJTs. Peter? Okay, so does that have anything to do with the fact that the Fermi level is in the valence band here? Yeah, it so is your question why is this flat here? Because there's so many. Okay, why the electric field, or, okay. It doesn't matter how heavily doped the base is. This energy band diagram, the conduction band, the valence band edge will always stay flat. So, yeah, the heavy doping, the degenerate doping of the base doesn't really make a difference. And that is a good point. So this base is degenerately doped. Look at this emitter. It's not degenerately doped. So you would normally think, well, that should give you really poor emitter injection efficiency and poor gain. But no, it's not, because you have this Ni squared, advantage, right, this ratio. So this way you can dope the base very heavily. And from this diagram, you can see the base is the narrowest region here. And you have to get the current into and out of the heart of the transistor here. And so the base resistance is actually can be a problem. And so if we can dope the base degenerately, that's a big advantage to make it less resistive. Okay? And that's one reason. So basically, these HBTs are pretty much what the industry uses if they want to have high-frequency amplifiers and so on. Okay, so this is just a simple example. Maybe I'll let you look at it on your own. But basically, it's just a simple example of saying, okay, let's compare like 3 BJT designs. One where the emitter is pretty heavily doped. Okay, let's see what happens if we really dope the emitter very heavily to try to boost the gain. And it turns out that, okay, if we dope the emitter very heavily, well, it turns out even though the ratio of NE to NB goes up, the gain goes down from 20-something to 2. I mean, reduces by a factor of 2. And that's because of band gap narrowing. Okay? But if you actually try to just have a reasonably, let's go back to reasonably doped emitter, and just have a band, a silicon germanium base. So we have, Ni squared increase because the band gap is smaller in silicon germanium by only 60 millielectron volts. We can actually increase Ni by a factor of 10. Right? So it's 10. It's 60 millivolts per decade. Okay, it's the same, right? Ni squared is proportional to Eg over kT. Anyway, so again, 60 millivolts per decade. So if you have a 60 millivolt smaller base region, band gap in this base region, Ni squared is increased by a factor of 10 in the base region. So you can actually boost beta by a factor of 10. Okay. Okay, so qualitatively, does that make sense to people? Great. Okay, so that's it in terms of modern transistor structures. So just a few, so the remainder of this class is just going to be, okay, so we've covered equations for current as a function of voltage applied, but that's in steady state. So finally, let's see what happens if we try to have things change over time. Okay, so we need to go over a small signal model and transient response, and that'll be it. So to understand the transient response, it helps to look at the transistor as reservoirs of charge. Okay, so just like in a p-n junction diode, we actually looked at charge stored in the quasi-neutral regions and used that to help us figure out how the voltage in a diode changes with time if you suddenly change the current. We have to do the same thing here. So the charge control model for a BJT, you can think of it as it's pretty similar to that for a p-n junction diode, except now in the quasi-neutral base. Okay, so we have emitter, we have base, we have collector. Okay, and then there's of course depletion regions here. So we have excess carrier concentration. So this is the excess, let's say, we're going back to PNP transistor. So this is the excess carrier, minority carriers in the base as a function of distance. And you have a quasi-neutral base width here. Okay, so basically we're asking, okay, let's consider how much excess minority carriers are stored in the base. And we know if the base is really short, much shorter than the average diffusion length, it's just going to be a straight line, right? Going from one value at the edge of the emitter depletion region down to essentially 0. Right? The excess carrier concentration will go to 0, or be slightly negative, right? At the collector depletion region. So we can easily determine. Okay, so the area under this triangle is this area here. You just use the 1/2 times the height times the width. It's just the area of the triangle. So you end up with this equation for the total excess minority charge stored in the base. Okay, and if that's not changing with time, then the base current that flows. Okay, so this is now a little confusing, but let's assume that. Okay, so this is for this charge control model to work, we have to make this basic assumption, which is actually not that accurate today. But if the base current primarily supplies majority carriers, to the base region. Okay, it always does that. But for recombination, with injected minority carriers. So This charge control model that we're showing here, this equation only holds if that is the primary, if IB, if the current that we're supplying to the base is primarily used to recombine with carriers with injected minority carriers in the base, okay, then this equation, this differential equation, will hold. Okay, so this is the same, analogy of the water tank, where you have QB, and you have some, leaking out due to recombination, and you're injecting them with time. So this would be dQB. Oops, sorry. Yeah. So anyway, it's the same kind of analogy as before. So basically, what you're saying is, if the charge stored in the base is not changing, then the only base current that flows is that needed to just supply to maintain the excess carrier concentration in the base. So as a carrier dies due to recombination, you're supplying. Basically, that's what the base current is doing. It's just supplying carriers once in a while to recombine. Okay. So this is a very simple equation for the base current, and let's also look at. So that's so there's two characteristic times. Tau sub b is the lifetime, minority carrier lifetime. That's one characteristic time constant in the base. The other one is the transit time. So the transit time is, like in the p-in junction, we talked about this. The amount of time it takes for a carrier, injected minority carrier in the base, to actually move and move across the base and be collected. Okay, so injected minority carrier will diffuse because of concentration gradient. It will diffuse across the base and get collected by the collector. Now, how much time does that take? And it's exactly the same as the way we derived it for a p-in junction. The amount of time it takes is going to be dependent on how fast it diffuses inversely. So the higher the diffusion coefficient, the shorter the transit time. W squared, so the width of the quasi-neutral region, the shorter that is, the shorter the time it takes for the carrier to diffuse across the quasi-neutral base region. So do you remember why it's W squared, not just W? Okay, so the shorter the distance, the less the time it takes. The slope, that's right. The slope, so the excess carrier concentration goes to 0 over a shorter distance if W is shorter. So that's why it's W squared. Okay. Actually, this looks, yeah, that's right. Right, okay, that's right, looks right. Okay, so an interesting relationship is that tau b is approximately equal to beta times tau t. So just to give you an idea, beta is typically about 100, okay? And so the ratio, it just turns out that the average time it takes for a carrier to recombine in the base, you can estimate it from the transit time. It's just going to be beta times the transit time on average. So the picture here is that you're injecting carriers into the base. Okay, so every once in a while, so a carrier a minority carrier in the base will recombine, but basically you're going to have like 100 carriers make it into the collector for every carrier that recombines in the base. Does that make sense? Okay, so basically carriers spend less. They travel pretty quickly from the emitter to the collector. So basically like 100 times more of them get collected rather than recombine, right? So you basically have 100 carriers that travel across the base in the time it takes for one carrier to recombine in the base. Okay, so that's basically some interesting thing that you notice from the charge control model. Okay, so we mentioned this only because I want to come back to the built-in electric field. So how much help does the built-in electric field provide? Okay, how much difference does that built-in electric field provide? So this slide just reviews, okay, if you can actually somehow have an electric field in the base, either by changing, okay, so realistically, the lower, this case 2 is what is used in real life. So you basically have a silicon germanium base here. Okay, so let's see, how much difference does that built-in electric field make? And so remember, the built-in electric field is just going to be equal to this change in the conduction band edge divided by Q to get out the to convert electron volt to volt, and then this distance here. Okay. So interestingly, for just a simple example, if we have, let's say, a base width of 0.1 microns and a typical diffusion coefficient, turns out that the base transit time is on the order of a few picoseconds. Okay, so an order of magnitude you should know. If I ask you to just estimate the base transit time or the transit time in a p-n junction diode, it's on the order of picoseconds. Okay, so the question is, how strong does that electric field have to be to cause the drift velocity to, I mean, if a carrier is drifting across the base rather than diffusing across the base, how high does the electric field have to be to make it drift faster than it would diffuse normally? Okay, so it just turns out then that the electric field should be greater than on the order of a kilovolt per centimeter. Okay, so let's see. So for W is 0.1 microns, delta EC equals 60 millielectron volts. That's going from, so that's a difference in, delta EG, sorry. Delta EG is 60 millielectron volts. This is 10% germanium. Okay, so if you have 10% germanium, that will have a smaller band gap by only 60 millielectron volts. Okay, 60 millielectron volts in, oh, okay. Okay, so what this means is if your base width is 0.1 microns long and you have a 60 millielectron volt change in the position of the conduction band edge, you can get this electric field strength. Okay? Does that make sense? So in other words, it's not that much. You just have to grade from, let's say, silicon to 10% germanium if you go from the emitter to the collector side of the base. And you can get this built-in electric field, which will actually help, right? It'll help to speed up the rate at which electrons move from the emitter to the collector. Okay, so so you don't need that much germanium. Well, 10%, atomic percent is significant, but it's not like you have to go to pure germanium to get some benefit. And the lattice constant for silicon germanium, well, the lattice constant for germanium is much larger, like 4% larger than silicon. So it's hard to grow germanium directly on silicon. So it's good to just grow a little bit of silicon germanium with small germanium content so you can maintain the crystalline structure. Okay? All right, so qualitatively, I think you should be able to calculate or estimate the base transit time. You know, maybe this is fundamentals, right? How long does it take for a carrier to drift a certain distance under the influence of electric field? So you should be able to understand these qualitative features of the heterojunction bipolar transistor. Okay? Any questions? Okay, so finally, let's move to, let's see, today's 28, lecture 28. Okay, I don't think I have it up here. Okay, so small signal model. So a small signal model is just designed to help you predict. Okay, so this is really primarily of interest for analog circuit applications. In other words, like an amplifier. So we derived this earlier in this lecture, but the collector current that flows in a forward active mode is roughly equal to this the saturation current of the emitter junction. Well, just the one part of the saturation current here. So this is from the Ebers-Moll model. Okay, but anyway, so some saturation current level times e to the q VBE over KT. Right. Okay. So what does the, so we never plotted this, but let's plot IC as a function of the input voltage, VBE. So it'll look something like, let's just worry about forward active mode, so it's forward bias here. It'll be an exponentially increasing function like this. Okay? So when you operate a transistor as an for an amplifier circuit, you basically operate in active mode. So basically the base emitter junction, oh, okay. Okay, so now we're talking about NPN BJT, given these symbols here. Okay, so we operate in active mode for an amplifier, and so that means the emitter junction is forward biased. Okay, so we're operating somewhere on this curve. So let's just say it's here, for example. So the small signal model is intended to help you determine, okay, if you actually increase, if we increase the base emitter voltage by a small amount, kind of a small amount, how much, okay, I guess didn't draw it enough, how much, so this is the little VBE, okay, so if we increase, so we're operating at some quiescent point, some DC operating point, and the question is, if we increase the base emitter voltage by a small amount, how much will the collector current increase? Okay, so that's defined to be little IC, right? So little VBE is just a change in the base emitter voltage, and little IC is a change in collector current. So that is the purpose of the small signal model, is to relate these small signal parameters to each other. Okay, so it's only related. It's only regarding. It only helps you to predict changes in current or voltage. So that's different than the Ebers-Moll model, which tells you, okay, if you apply a certain voltage, these voltages, how much current is going to flow. Okay, so the Ebers-Moll model is kind of like a steady state DC model. Okay, so for amplifier applications, what we want to know is how much change in the collector current will we achieve, will result if from a certain change, from a small change in the base emitter voltage. In other words, for a small change in input voltage, how much change is there in the output current? And so that's the definition of transconductance. So essentially, this is the way I define things. This is the same as little IC over little VBE. Okay? Well, we can just take the Ebers-Moll equation there for IC, take the differential with respect to VBE, and we can end up with simple expression IC over the thermal voltage, KT over Q. Okay, so remember, KT over Q is just 60 millivolts at room temperature. Okay? All right, so what does this mean qualitatively? It means that the transconductance will increase with the bias current, the DC bias current. Right? So you're here at this, operating at this DC bias point. So the higher up on that curve you operate, the higher your transconductance. So hopefully that makes sense, because if we're operating up here and making a change, the slope of this exponential curve gets steeper, right? So you'll become more sensitive to changes in the base emitter voltage. Okay, so qualitatively, hopefully this makes sense. If you operate at higher current, you're going to get steeper change in current for a given small change in voltage, input voltage. Okay. Just curious, how does that compare with a MOSFET? Do you remember transconductance for a MOSFET? Just qualitatively, is it exponentially dependent on the input voltage, the transconductance? Quadratic, yeah. So it's like quadratic, or for a short channel MOSFET, it's linear. Actually, wait. For a MOSFET, it's also linear. For a long channel MOSFET, it's linear, right? Because if we take, for a MOSFET, GM is defined to be the change in the output current, which is ID, for the change in an input voltage, VGS, and that's equal to, it's W, even for a long channel device, sorry, not 2, ML VG minus VT, right? I'm just reminding you. So it's actually linearly. So it's VGS minus VT. So this is the fundamental reason why a BJT is actually better than a MOSFET for amplifier applications. So if you have like discrete transistors in the lab, BJT or MOSFET, you'll have higher gain if you pick the BJT. Okay. All right. Okay, so that's to predict how the output current will change for a small change in the input voltage. But we don't care only about gain. We care about like power consumption and speed. Okay, so that to figure those aspects out, we need to know these input small signal parameters. Okay, so for a BJT, if you change the input voltage by a little bit, you're going to, well, I mean, okay. So you basically are going to change the okay. So what this input circuit models is the base emitter junction, right? Essentially, right, we have the base emitter junction. So remember the small signal model for a PN junction diode? It has some small signal resistance, which is basically the inverse of the slope here. Sorry. It's not that slope, it's this slope. So if you plot IB versus VBE, right, so this is for the input circuit, right? For the input circuit, you're plotting, what matters is current versus as a function of the voltage here. Okay, so the curve that makes sense to look at is this exponential curve. So, okay, this computer. So it's an exponential curve, again, for the input circuit, right? It's just a base emitter junction. So basically, the slope, so if you're operating at a certain VBE, the slope is basically 1 over R pi, right? So the change in this, R pi is just the ratio of VBE. R pi is VBE over IB in steady state. Right. So the slope of this IB versus VBE, that's going to be your R pi. And then C pi is just going to be your base emitter junction capacitance. Okay, so that's basically what's shown here. If you take the derivative of the input current with respect to the input voltage, it turns out because you have beta as the ratio of IC to IB, you can write R pi as a function just in terms of the transconductance and beta. Okay. Now C pi is the PN junction capacitance. So remember in the active mode, the base emitter junction is forward biased. So under forward biased, you have the diffusion capacitance. So if you change the voltage across a PN junction, you have to change not only the width of the depletion region, so therefore the charge stored at the edges of the depletion region, but you also have to change the amount of excess minority carriers on each side of the junction, and that results in this diffusion capacitance component. Okay, but under forward bias, right? Oops. So the reason why this is dominant, okay, so this is dominant since the emitter junction forward bias. So remember, the charge stored in the quasi-neutral regions increases exponentially as you forward bias the PN junction more and more. So basically, the diffusion charge dominates. So for simplicity, you can, if we have this in a homework problem, basically you can just assume that C pi is equal to the diffusion capacitance of the PN junction, the base emitter PN junction. Okay, so here's a new, yet another new term here. So QF is the charge, the magnitude of charge stored in the quasi-neutral regions, either on the base side or the emitter side. They're equal on both sides. They're balanced. So the forward transit time is defined to be QF divided by IC. Okay? So if we define this, if we introduce this new forward transit time parameter like this, we define it this way, then the diffusion capacitance is going to be just equal to tau F times GM. Okay, but this is the time, qualitatively what this means is this is the time, required for, the reason why it's called forward transit time is because it's the time required for the minority carriers, to diffuse from the quasi-neutral emitter to the quasi-neutral collector. Okay, so basically, it's longer than the base transit time. Okay, the base transit time is the amount of time it takes for the minority carrier to go from to go across the quasi-neutral base. The forward transit time is longer than the base transit time because it starts at the edge of the depletion region in the emitter, and it ends at the edge of in the collector, the quasi-neutral collector. Okay. Okay, so here's just a simple example. A typical level of current in an integrated circuit might be 1 milliamp for a BJT, any transistor. And so transconductance is on the order of millisiemens. R pi, if you have a gain of close to 100, is on the order of kiloohms. Okay? And input capacitance is typically on the order of tens of femtofarads, depending on the cross-sectional area. Okay? Anyways, very simple example here. All right, so if we use a transistor as an amplifier, at some point, so the amount of current, if you want to change the input voltage very quickly, that means you have to change the charge stored in this capacitance more quickly. So that means you have to supply more current. So eventually, your input current is going to get to be kind of large, and so you're not going to have significant current gain. So the ratio of IC to IB actually at high frequencies is not going to be greater than 1 anymore. So you'll have no current gain. So the cutoff frequency is defined to be the frequency at which you actually have a current gain of 1. So the interesting thing to notice then is it's just 1 over the forward transit time plus this other term that usually should be kind of small. Okay? But bottom line is you would like to minimize the forward transit time to allow your transistor to amplify signals at higher and higher frequency. So similar to the MOSFET, the cutoff frequency for a MOSFET is sort of related to how much time it takes for it to go across from the source to the drain. Okay, I think I'll skip this part, but okay. If you take into account parasitic resistances and all that, then the equation for the cutoff frequency is a little bit more complicated. Okay? All right. And the Kirk effect, so this is just to explain why at high frequencies, the cutoff, at high current levels, why the cutoff frequency degrades. Okay? And the bottom line is over here, tau F increases. Okay, so the forward transit time actually increases if you operate the transistor at too high of a current level. And the reason for that is just qualitatively, if you have a very high current level, that means you have a large current density. So actually just the current that's being collected by the collector, let's say the minority carriers, this is for an NPN transistor, I believe. Yeah. So basically you're collecting electrons in this N-type collector, and because the current density is so high, just the electrons that are moving through provide sort of result in charge that's even greater than the depletion region charge, right? So the depletion region exists because you have ionized dopants, ionized donors. But if the electron concentration, just due to this current, is significant compared to the carrier, to the dopant concentration, then actually what happens is that effectively your depletion region no longer exists, and it actually moves out. And so so the distance between the quasi-neutral emitter and the quasi-neutral collector actually grows if you go to very high current densities. And so the forward transit time increases, and the cutoff frequency decreases. But just qualitatively, just know that at very high current levels, the cutoff frequency goes down. So in other words, you can't really amplify too high of a current if you want to go to very high frequencies. Okay? So just qualitatively, you should know that. Okay, let's just end here. So for transient response, what you need to know is basically you need, in order to have a transistor turn on and reach steady state, you have to sort of fill the quasi-neutral base region with excess carriers. Okay, so remember for a BJT, if we look at the output current versus the output voltage, it looks something like this, right? For different values of IB. So for switching applications, what we're doing is we're actually switching from high output voltage when there's no current flowing to low output voltage at high current. Right, so we're switching. So when the transistor's off here and it's on here. So when it's on, we want a small voltage drop across the collector and emitter, right, across this transistor. When it's off, we want no current to flow, and there will be a high voltage dropped across it. Okay. All right, so here in the on regime, the transistor's operating in saturation. In other words, both the emitter junction and the collector junction are forward biased. Okay? So in steady state, the excess holes in the base look like this, right? So it's basically greater than 0 because you have a forward biased collector, and it's greater at the collector junction. It's greater than 0 at the emitter junction because you also have a forward biased emitter junction. So this is the steady state. The question is, if you start in cutoff, where essentially you have no excess carriers, okay, and you suddenly force current to flow in the BJT, well, how does the charge eventually reach this profile here? How does the excess minority carrier charge stored in the base actually reach that steady state? Well, it turns out that the base current slowly increases. Okay, so the slope here slowly increases, and eventually it'll reach a slope, the correct slope, dictated by the circuit. And then after that, the excess carriers will build up like this until it reaches the required values set by the circuit, by the bias voltages determined by the circuit like this. And then when you turn off the transistor, you have to, so it goes up to here. And when you turn off the transistor, you have to wait for the charge to die out, let's say due to recombination or diffusion out, die out to this level here, and then the slope will decrease down like this. Okay, so qualitatively, there's going to be a storage delay time just to be able to charge up the quasi-neutral base to the level required by the circuit in saturation mode. Okay. So I think all you have to know qualitatively is that the amount of time it takes for the transistor to respond to changes in the circuit, the switching circuit, depends on the minority carrier lifetime, tau sub b. Okay, so basically, the shorter tau sub b is, the faster you'll get charge to build up or die down. Okay, and the more, let's see. Okay, so this storage delay time. Okay, well, let's just say qualitatively. Let me explain. Okay, so the final thing is right here. So this actually takes extra time right here to go up and down, right, to turn on and off the BJT. So one trick that people sort of have developed in the industry is to insert a Schottky diode, okay, Schottky diode right here in series with the collector-based junction, okay. So what that does is that when this collector emitter voltage gets too low, okay, then this Schottky diode will actually start to turn on and conduct current. So instead of having current go through the BJT, current will flow through the Schottky diode. So the Schottky diode actually limits how much the BJT can go into saturation. So that's kind of hard to explain right here, but okay. So basically, it prevents this output current, this output voltage, from getting to be too low, and so the transistor actually stays closer to the active mode of operation rather than going deep into saturation. So that way you can actually get the transistor to turn off more quickly if you have a Schottky diode in parallel with the base collector junction here. Okay, so the key is to reduce the charge stored in the quasi-neutral base if you want to maximize the speed at which the BJT will turn off. Okay, so qualitatively, just similar as for a p-n junction diode, you just want to minimize the excess charge stored in the quasi-neutral region of a BJT if you want it to turn on faster or turn off faster. Okay, and to have a smaller, steeper exponential curve, you can reduce the minority carrier lifetime, and you can purposely introduce impurities into the base region to kill the lifetime so carriers recombine more quickly. And so that is done, but what is the trade-off there? What happens if you, if you decrease the minority carrier lifetime in the base, what's the trade-off? So to make it turn on and off faster? The gain, right? So the transport factor degrades, right? So you'll have, as you inject carriers from the emitter into the base, more of them will recombine in the base. They won't get collected, so the gain will go down. So the trade-off here is reduced gain, but you have faster transient response, so the BJT can turn on and off faster. Okay. All right. So for the final exam, just qualitatively understanding these things. I'll go over some sample questions in the review session. I think qualitative understanding of transient response, small signal, gain for a BJT is all you need to know. Okay. All right. But I think based on the quiz, you actually, most of you do know the MOSFET pretty well, so that's good. Okay, because the MOSFETs are unfortunately more important for ICs today. But it is good to understand how BJTs work as well. Okay. All right, that's great. So I guess I'll see most of you, if not at the final. Okay. Anyway, I hope the rest of your classes go well, and I look forward to seeing you at the final. I hope you do well. All right, take care.